to set up our allocator using the strategy, that means our initialization function needs to start out, we start out with the breakpointer somewhere. We're first going to make room for a block header and set up the initial block header. So initially we have an empty linked list. The only header we have is the terminator header. Right, so that's where we set first BP to be the current break and initialize that header so that our picture looks like this. Now at this point, when there's an allocation request, we will need to get more memory from sbreak, and we'll make that the job of extend. So extend job is to get at least new size bytes. We'll align that to the chunk that we've chosen for asking for sbreak chunks. And we will set BP to be the new break, set at BP actually to be the old break as we increment break. So BP will be right here. When we first start out, BP will turn out to be the same as first BP. After moving the breakpointer, so our job then is to fix the size on this block, which now has the newly allocated range, and install a new terminator here. So fixing this block means we take BP, get its header, and set the amount of memory we just allocated. Right? So if our chunk size is 6 words, then we put 6 words there. And let's see, it's unallocated right now. And then we also need to set up this terminator right here just before break, but that corresponds to following to the next block payload, getting that block's header and setting it to be a terminator. So double check that all the arithmetic and offsets work out right here, but that's how we extend things. This is what the picture looks like when we start out, but we could also call extend we're in the middle of things. Like suppose we have a bunch allocated. All we have at the end is a block of size 3 words, and we want 4 words or 5 or something like that. So the same thing's going to happen. Break's going to get incremented. BP is going to be the old break. Then we're going to fix up the header here to say 6 and install a new terminator. So now extend has just made it so that we have a big enough empty block that we can allocate from. Malloc's job is to use that or find something earlier. So recall that we set first BP to be a pointer to our very first block's payload. So we can just walk down our linked list as long as we haven't hit the terminator, as long as we haven't hit a block whose header has a size of 0. If we have a header that's not allocated yet, so this one will be allocated, we'll skip it, we'll follow here. If it's not allocated, and if it's big enough, then we'll decide to allocate from that block pointer for that payload pointer and return it. Otherwise, we'll skip to the next thing in the linked list. If we get all the way down to the end, if we do hit a block whose size is 0, that's when we extend, and then because we're extending from here, that means we're going to allocate right there. We know we've made it big enough by extend, and just return that block pointer. The job of set allocated is mostly to change this unallocated bit to an allocated bit, but it also has to do the work of splitting. So suppose we're in this situation, we've decided that we can allocate at this 5-word block. That means the size here must be 5 words or less. If it's too big, if we need 3, well, let's see, if we need 4 words, and if we tried to make this its own block, it would be a useless block. It would be a block of size 1, which means its payload is 0. So we won't try to split in that case, and we'll have some extra unused space at the end of the block. If the size we wanted is exactly 5, of course, that's great. If the size is 3 or less, then it could be worthwhile to split this block. We can set the size to 3 in addition to setting the bit. And so that's what you see here. We find out how much space would be left. As long as it's useful space, that is, it could accommodate a request for 1 byte, then we adjust BP size to be the size that we wanted. We set the size in this next pointer to be the size that's left over, and that next pointer is unallocated. And then finally we mark the block as allocated. Note it's very important that we set the size on the BP before we try to get the next BP. That was how we got to the right place here. And finally, to free a block, this was the whole point, being able to free blocks. To free a block, when you get that block pointer, you just get the header for it and set the allocation bit to 0. So I've set up this implementation as implicit, just extracted all the code from the slide. So you can see it's all what we had before, and it's called implicit for reasons that we'll explain it. But if I build it and try running it, then you'll see that everything passes. You also see that it's quite a bit slower than our old implementation, and we're going to talk about why that is eventually as well. It's slower because to allocate, it has to look a lot more instead of just incrementing s break.